Now, one thing that is apparent in looking at this picture is that although we have changed the shape of the waveform by adding in these different waves, in this case three different waves together uh, with different amplitudes, um, the net waveform is still periodic. Okay, so these two waveforms are still periodic with they still have they still repeat. It still repeats with a every 2 pi over k1, every lambda 1 wavelength. You have the same form, but we certainly have changed the waveform. So if we want to talk about wave packets, okay, then we have to figure out a way to actually get rid of the repetition, okay, these these beats, if you will, okay, and actually just uh, uh, be left with a single pulse, okay. So how does that work? Well, if we imagine again that we have a single waveform, I mean a single component wave, so this has a single wavelength, one value of k naught, okay. It's a single harmonic wave, and you can see basically it will repeat for all time, all right, or in all space. Um, if we add a couple more waves to that with smaller amplitudes, one on either side of k naught, then we can get this waveform here can be modulated, uh, and we get beats basically. Okay, and you can see now that we're starting to suppress the amplitude of the waveform in these regions between the beats. And if we add in several more waves, again spreading out the range of k. Okay, so now we're going even wider in k compared to um, compared to what we had over here. So if you traced this up, we're now covering a wider range of k than we were before. We have more waves, and that basically uh, allows for more opportunities to have uh, destructive interference. And so now you get a bigger region where the wave amplitude is suppressed, and now you have beats, but they're spaced further apart in space. And again, if you add in more waves and broaden the distribution even more, then you suppress more until eventually, if you basically have an infinite number of waves of wave numbers, or yeah, an infinite number of waves with different wave numbers in a continuous distribution, which is what's represented here, then you can push all these you can push all the beats basically out to plus or minus infinity, and you're left with a single um, pulse, or a single wave packet, okay, where the amplitude is essentially zero everywhere else and is only appreciable um, in in this one region, which corresponds to a particular value of k naught. Okay, so if we look at this again, so we start from a single harmonic wave, and we add in a few, in this case, two extra waves at different wavelengths and different amplitudes, then we get beats. We get fewer beats if we add in more waves. We get fewer still when we add more. And then finally, if we have a continuous distribution, we can get a single wave packet. Okay, and what I've actually drawn here is a special distribution of k values. It's a Gaussian distribution of k values, and it's characterized by a width in k space. That is a width in the range of k values that appear in this distribution, which we call sigma k. And this kind of plays the role of delta k that we discussed in the previous lecture, the uncertainty or the spread in the k values, okay, in the wave number values. And analogously, in real space, in the actual physical space in x, you have a spread um, in the in the size of your wave packet. You have um, an actual spatial distribution in your wave packet, which is characterized by sigma x. And again, this plays the role of delta x that we discussed in the previous lecture.